Hello, can everyone hear me? Excellent, thank you, Ashley. Um, how do we, how many people do we have with us? I think people are starting to roll in. Oh, one day I'll get used to this YouTube. Thanks, Ashley. Oh, yeah, we're updating 3 views. Okay. It will give people a little bit more time to join. I admit 6 p.m. is a bit rough, but I thought if I'm going to record a lecture, I may as well live stream it and have it record for me. And then for those who want to join, are able to join and chat and comment and contribute. Could I get a comment in the chat from a student though, please? Hello, Caden. Hello, Kianan. I think we're up to 8. Right. Maybe everyone's a bit used to me starting at 5 past, because that's when the recordings in the lecture theatres start. So that's why I need to wait until then. Right. Right. Yes. Let's make a start. Okay. So yeah. So welcome to your makeup lecture. So this is technically lecture 2 for week 4. And we're going to continue on talking about bitwise operations. Okay, but first, as always, we start with some announcements. So remember the week 3 test due today at 9 o'clock. Well, maybe that's why we have little turnout on the live stream. Census date as well, so that's today. This is your last chance to drop courses without financial penalty for T3. So that's at midnight. And assignment 1 due, don't forget we have an assignment that's due week 5, so next week, Friday, 6 p.m. And I'm expecting that the help sessions next week are going to start getting busy as everyone's starting to realize that their assignment's due and they need to get started with that. Okay, the only thing I like less than talking about plagiarism in lectures is talking about plagiarism one-on-one after the lectures with students. So bear with me. So please remember to get help from the right places. So staff and lectures, tutes, labs. We have the forum as well. That is a fantastic place because not only can you ask questions, but other students can learn from your questions and the answers. And it'd be great to see some great discussion on the forum. Really, you can post about anything COMP1521 related. Okay, we've got the help sessions as well. If you need help, please go to the help sessions, and revision sessions as well. We had a C revision session. I believe we'll have a files revision session later on, though we haven't covered files yet, so that's still have some time before that. Okay, but do not get help or submit code from external sources, in particular ChatGPT, but also external tutors as well for other courses and other people's code as well. Okay, so we do run plagiarism checking on all the submissions. So unfortunately, we tend to wait until the end of the course before we run the plagiarism checks on all of the submissions, all the way back to Lab 1. So yeah, so please don't think that just because you plagiarized a little bit in Lab 1 and you weren't warned about it, don't escalate, because we do run all our plagiarism checking at the end of the course. So today's lecture, so we're going to be doing some recap exercises on integers. So normally there's a little bit more time between these lectures, but I think it's important to do these recaps, particularly on integers, because I think a lot of people haven't thought about integers as a sequence of bits like we've been thinking about them, or we were thinking about them yesterday. And then we'll continue on with our bitwise operators. So we covered briefly the bitwise and, bitwise or. We'll cover those in a bit more detail, and then cover the remaining set. Okay, so integers. So recall that we have our bases here. So these tables represent the placements of the digits here. So everyone's familiar with base 10. So we'll start with that. So the first column is the ones column. The second column, the tens column. So that will tell us the number of tens in this number. The hundreds column tells us the number of hundreds, and the thousands column tells us the number of the thousands. So there's 4,000s, 700s, and 5. There's no tens. And we can reconstruct the number, or we can split the number into its individual components. 4,000 plus 700 plus 0 plus 5. But that's not very interesting. So when things get interesting is when we start looking at other bases. Okay, so in this case, this is base 16. So the first column is the number of ones as usual. Second column is the number of 16s in this number. The next one, the number of 256s, and then 4,096s. Okay, so but we follow the same process here. So for this number here, 3 times 16 cubed plus A represents 10 in hex, so that's 1 above 9, and we multiply that by the next column, so 16 squared, and we keep going. 15 times 16 and 1 times 1, so 16 to the power of 0 is 1. And when we add all those individual components back together, then we get our decimal value. Okay, but what does this number represent? What do you think? So before you work it out, well, we can't know without knowing the type of this number, right? So is it an int? Is it an unsigned int? Is it a float? Is it a Unicode character? So float and Unicode characters are things yet to come in the course. But MIPS instructions you're pretty familiar with. So is this a MIPS instruction? How do we know what this number represents? Okay, so so this is relevant to bitwise operations, and I'll explain that later on. But suppose we have this MIPS instruction. Remember, each MIPS instruction is 32 bits wide. So this is the instruction represented in hex. So how would we work out which MIPS instruction that is? Okay, so yeah, 32 bits long, specifies an operation, 0 more operands, and we have the 3 different types here. So the R type, which has the operation on both the left-hand side and the right-hand side, these 12 bits together, and the 4 registers, or potential registers, that this R type instruction could execute on or could operate on. And similarly the I type, which has only 2 registers but then a constant, and the J type, which has just the 1 register and the rest is left for the address. So how would we decode a MIPS instruction? So so for example, like the purple here would represent an opcode, and the blue here would represent one of the first register R1, and um, green the green digits here would map to the next 5 bits here for, well, it'll be this one here, for register 2, and the brown will be the constant. So in this case, this is an I type. Okay, so after running through that example, how would we work it through for our how would we work it out for our original instruction? So the first step here is to take our hexadecimal number and split that up and convert that to binary. So remember, that's a really easy process because each hexadecimal digit corresponds to 4 binary bits. So we can take each of these digits and easily translate this down to binary, especially if we have a table that lists all the conversions. But in this case, it's pretty simple: 0, 1, 2, 8, 8, 8, and 2 and 0. Okay, but our MIPS instructions, they're not in groups of 4, right? So if we look back here, this first group here is a group of 6, then we have a group of 5, 5, and then for this particular instruction, we have a group of 16. So we want to do the same with our binary numbers here. So that's why converting to binary was important. So when we group these up, we can see the 6 bits here and the 16 down, 2, 4, 6, 11 bits down here representing the other part of the opcode, and then we have 3 registers in this case. So we can find this structure by, if we look at our MIPS documentation, which I should have handy. So our first digits were all 0. So here we can look and see that there's a number of instructions that this could be referring to, right? So we do need to look at, but they are all of the R type. But we do need to look at the remaining bits of this opcode to know what the instruction is. Okay, so we need to look at these 2 parts here, but then we've grouped our other bits to represent the registers. So from that table again of all the instructions, we can look this up to be an add. Okay, I should have split screen these. Okay, so one thing to highlight here is we have the add. So when we're writing our MIPS assembly, we're expecting the RD, then RS, then RT, but they're in a different order over here in the bits of the instruction. So we need to take RD first, which is the third one, then RS and RT. Okay, so we take RD, and so this is the number in binary. This represents 17 in decimal. So we have register number 17 that we can put down, then register 9 and register 8. But we don't like to use these register numbers. We prefer to use the symbolic names for them. So from our MIPS table again, where are we? We have our list of registers and their corresponding symbolic names. So we can map those to provide a more meaningful assembly instruction there. Okay, so let's check that we have got this correct. Just go into MIPSy web. What do I have here? Okay, so we have our main. I'll put the .text in there. Okay, so remember, in our code we can just use the directives that we would normally use for the data section, and we can just paste our instruction in there. Save, and if we look at our decompile code, so we have This is the original machine code here, and this is what it would get decoded to. Where are we? Okay, but this is exactly what's happening in your CPU, right? The CPU gets this instruction and it pulls out these bits, and it routes them to the different parts of the CPU. So these bits here will be used to select the these bits here will be used to select the target register for whatever the ALU was being told to do, and these two here will be choosing the input registers for the ALU, and these bits here will be telling the ALU what operation it should be performing on those registers. So whether it's an add, subtract, etc. Okay, and our MIPSI emulators, they're doing this as well internally in C code. So they'll take this MIPSI instruction and they'll use bit operations to extract the relevant parts from this hexadecimal number. Okay, so we talked a bit about endianness last lecture as well, and in the lecture previously actually. It's quite an important topic. I'm just going to run over it real briefly. So the big points to note here is that the endianness is all about the order in which we store a number as bytes in memory. Okay, so for the big endian, the big part of the number is first in memory, and for the little endian, the little end of the number is first in memory. Okay, we talked about loading bytes and half words as well, and this was in particular to do with signed and unsigned integers. So remember we had the LH and LB for signed values. So in this case, we're loading a value into a 32-bit register that's shorter than 32 bits. So given that this is a signed value, we need to take the signed bit, whatever that is, and extend that through so that the equivalent 32-bit value represents the value that we're loading from memory. But in the case of the LHU and the LBU, so these do the same thing, but they don't have to extend that signed bit in any case. Okay, we actually looked at different branch instructions as well that depend on whether it's the outcome depends on whether it's it should be interpreted as a signed value in that register or an unsigned value, because the value in the register, there's no notion of whether it's signed or unsigned. It's all about how we use that value. Okay, so just some brief examples again of how we of what happens here. So if we have the LH, which is the signed version, this is little endian MIPS, so this is the big end here at the end, and we can see here there's 5 will be 0101, so that first bit, the signed bit, is not set, so we don't need to extend it. But if we have a different value like AB, so A is 1010, so that signed bit is set. So when we're loading this half word in, we're sign extending that signed bit all the way up through this 32-bit register to ensure that it's still interpreted as a negative number. And of course, if we use the alternative, the LHU, this avoids there's no sign bit for an unsigned number, so we don't sign extend it even if that most significant bit is set. Okay, so we also looked at fixed size integers. So on depending on the platform that we're compiling for, the size of an integer can be different. The best example of this might be the size of a pointer. That varies quite a bit. So on 64-bit machines, it'll be a 64-bit pointer. On a 32-bit machine, it'll be a 32-bit pointer. But in this case, if we use this magical include stdint.h, we get all these types here that have a well-defined size. So so it doesn't matter um, what the machine architecture is. An int8 will always be 8 bits. uint64 will always be 64 bits, and we do have the signed and unsigned equivalents. The other quick mention I wanted to make is, again, this limits.h file. This one is easy to forget, but this provides all your constants for the maximum of each of these types. And keep in mind that these maximums can change depending on the machine that you're building for. So I think we take it for granted that an int is always 4 bytes, but that's not always the case. Okay, we looked at the representations of integers. So we had an int is represented as 4 bytes, which is 32 bits. So we looked at these integer values as if they're a set of 32 bits, okay, and how those bits would represent to a value. So for an unsigned int, all zeros is naturally the value 0, and all ones is naturally the maximum value that we can represent. In this case, 2 to the power of 32 minus 1. One thing I'll note here is that 2 to the power of 32 would be over here on the left, and when we subtract 1, we have to go all the way to that bit before we find one that is set, so that we can turn that into a 0 and then backfill all the rest of these ones to when we subtract 1. Okay, and then we looked at signed integers, and I guess the best way of looking at this is that we take the top half of our unsigned integers and we strap it onto the bottom of our number system. So where we had 0, when we subtract 1, we actually end up with all 1 set. And I wonder if I can get some interaction from chat. Does anyone remember what we called that form of representation? I can't tell if everyone's just being quiet or if there's just lag in the video. Alright, so it is called 2's complement representation. Okay, so onto bitwise operators. So it's a bit difficult to understand why bitwise operators are important until you start using bitwise operators. But they're used for optimization. So yesterday we looked at using bitwise operators instead of the modulo operator, because that modulo operator can be quite expensive for a CPU in terms of how long it takes it to execute it. Not every instruction in a CPU takes exactly one cycle to execute. Some of them need to be split into multiple cycles, and division and modulo are one of those. So we were able to optimize the modulo operator by using bitwise operators instead, and we'll see a little bit more about that today as well. Embedded systems, so these are typically used heavily in embedded systems for, well, first of all, the limited memory and all that to save space, and also for device drivers as well when you're interacting with the device or the peripherals that are attached to this embedded system. Data compression. So I had a really unfortunate experience recently where I was dealing with data that was 24 bits wide. So if you can imagine, that's not a 32-bit int, it's not a 16-bit int, it's right in the middle there. And they packed the bits of, so it was a stream of these 24-bit numbers, and they packed them all tightly into memory to save space. The main reason for that was not actually to save the memory, but actually when you're transferring this data from one subsystem to another, then you want to make the most out of that link to transfer that data across. You don't want to be sending numbers that are used just to pad something out from 24 bits to 32 bits. Security and cryptography. So usually we use the XOR operator for this, and that we'll get to later on in this this lecture. And for graphics, actually for the next lecture, I've got a really good example of how we use bitwise operators for graphics and computer network. So I already mentioned saving the number of bits that you need to transfer. So through our through computer networks, especially with our high-speed Australian NBN, but also for the headers that tell these packets where they go and what type these packets are. Then we want to pack as much information into the bits available to us, so we're not just sending useless information. Okay, and if you go on to do the operating systems course, so you might come across these coprocessor registers in the MIPS CPU that you'll be working with. So this is a set of, I guess you would call them like peripheral registers, device registers, and each of them have a specific purpose. Okay, and the one I'll take for an example is this TLB low. So you notice bits 0 to 7 in this register. They are always set to 0 according to this table. But then we have 4 flags in here, so the G, V, D, and N. And we might want to extract the value of each of these flags, or we might want to set these values of these flags, and we would use bitwise operators for that. And that's the same with the P page over here. Okay, so a recap of the bitwise operators. So we have the CPUs provide instructions which implement these bitwise operators because they're very useful. So they provide us a way of manipulating the individual bits of a value. And I think I was careful not to call it an integer there, it's just a value. So MIPS provides 13-bit operation instructions, and C provides 6 bitwise operators. And we're going to be focusing on the C at the beginning of this lecture, and moving on, we'll hopefully have some time to touch on the MIPS instructions for that. So we'll go into a little bit more detail about AND and OR, but then we'll be covering XOR, NOT, and the left and right shifts. So recap of the AND. So we're taking 2 numbers and we're taking the bitwise AND between them. So for each pair of bits, we're performing an AND operation, and the resulting value for that corresponding bit is only going to be 1 if both of those other bits are 1. Okay, so this is useful for checking if a particular bit is set in a value, or it can be used for unsetting these bits. So if we were to construct our second number to have a 0 here, we would be able to ensure that this value here is also a 0. Okay, so quick exercise. So given a bit value x, so any value of x, a 0 or a 1, what would x and 0 be? I think maybe everyone's eating their dinner and just coming along for the ride. That's okay. So x and 0, because we're ANDing with 0, this is always going to be 0. And for the next line here, because we're ANDing with 1, well, we don't know what value that's going to end up being. Okay, so because we're ANDing an unknown value with 1, well, it really depends on what this value is. So in this case, we just have to say that it's x. So why do we get 1 every time there are 2 zeros? Okay, so if we have 2 zeros here, so when there are 2 zeros, so we're looking at the columns. It's a horrible circle. we're looking at the columns here, so if we have two zeros, we end up with a 0. And sorry if that was referring to this slide here. If it doesn't matter what value this is, if we're ANDing with 0, then the result is always going to be 0. Okay, so just to extend this idea, so we can create bit patterns to help us to isolate the bits that we are interested in. And we call these masks. So generally these masks are a consecutive sequence of bits, but they don't necessarily have to be. So in this example, if we take the number 13 in hex, and this is the binary representation, our mask value of 7, which is 3 consecutive bits on the end here, when we AND these two together, so this forms a mask. So when we AND these together, so the only bits that we're going to keep are what's behind this mask here. So the 0, 1, 1, and everything else is just going to become 0. So this is how we can extract, as a concrete example, the register number from a MIPS instruction. Okay, so recap of the bitwise OR. So in this case, so all we need is, if we have two numbers, all we need is a 1 in any of these numbers for one of the bits, for the corresponding bit in the result to be 1. Okay, and this is great for setting bits. Okay, so if we have any given value x, okay, if we're ORing 0 into that, well, that depends entirely on what the value of x is. If it's a 1, we'll get a 1 at the end. If it's a 0, we'll get a 0 at the end. But for this one here, x or 1, well, it doesn't matter what x is in this case because the second number is a 1. So we'll always end up with a 1 as the answer here. Okay, and we can use masks with the OR operator as well. So for example, well, the same example, we have 13 as our x and the mask of 7. When we OR these together, we're setting all of the bits in the mask in that final result there. So it doesn't matter what we had in this orange region where the mask sits, we'll always have the values of that mask set in that final result. And the bits in front, so these are untouched by the mask because it's an OR operator, they just pass straight through to that final result. Okay, negation, I think this is where things get a little bit interesting and maybe a little bit easier as well. So for negation, we just take any single bit and the result for the corresponding bit is going to be the reverse of what that bit was. So 0's become a 1, 1's become a 0, easy. Okay, but this does not mean taking the negative of a number. Remember, it's 2's complement when we want to take the negative of a number. This is the bitwise negation. So remember, for the 2's complement, we did do a bitwise negation, but we did have to add a 1 on the end to do a true 2's complement representation. Okay, so bit masks, we can use the bitwise NOT with these bit masks as well. So you can use the same mask to both set and unset bits. So for example, if you have the mask of 7 and you're using the OR operator, it's going to set the least significant bits of the value, just like we saw in that previous example. So the bitwise NOT operator, the tilde, with that same mask, and use it with the AND to unset the least significant bits, least significant 3 bits. Right. So we have our same example here with OX13 and our mask of 7, but we're taking the bitwise NOT now. So instead of these 3 ones being set, we've inverted that mask so all of these bits are set. Okay, so when we AND with this mask, we keep all of the top bits here, and all of the lower bits become 0. We throw those away. And checking alignment with bitwise and NOT. So I've got this little example here where this is, for example, if you're using in assembly, if you're using your dotted line with the number 2, this would be the equivalent C code of that. So we're given an address. Let's suppose that that is the current address in the data section that the compiler is up to, and it's come across a dotted line, so it needs to align to the next 2 to the power of 2. Okay, so we'll take this pointer, and this is we're casting that to a uint pointer underscore t. So this is also another data type that's in that wonderful standard int library. So yeah, standard int header, sorry. So this is going to be, this data type is exactly large enough to store the value of a pointer, but then we can treat it as an integer. So let's first convert our pointer to an integer address. Okay, and now we want to check if we are currently aligned. So we're using a bit mask of 1, 1. So remember when we were looking at using these bit masks, or we're using the bit mask of 1 to check whether a number was odd or even. So a more general way of saying that is that we were checking whether a number was divisible by 2. So by having both of these bits set, we're checking whether a number is divisible by 4 instead. So of course, if we're already divisible by 4, we can just return that pointer. We're already aligned. But if not, then we want to advance to the next address that's aligned to 4. So we're going to take the bitwise negation, or bitwise not of this mask, and we're going to AND it with our address. And that means that we're going to take all those most significant bits and they're going to pass straight through. But the bits that represent the alignment of 4 bytes, so they're going to be set to 0. Okay, so we now end up with an aligned address, but that's not quite what we want. We want to advance to the next aligned address, but since we're already aligned to 4, we can just add another 4 on the end of that. And now we have the next address that is aligned to 4, that is divisible by 4. And of course we just need to cast that back to a pointer before we send it back. So I do have a little example of this in operation. Oh, I didn't show all of the code there. That should be big enough. All right. Okay, so we have this same aligns to function, and I've added a main in here that it really just it defines an integer on the stack, and then we take the address of that, cast that to a character pointer so that we can advance it 1 byte at a time. Okay, and our for loop here will go from 0 to 20, incrementing that address as we go. And we're going to print out the address, and we're going to print out what the result of align to is when we pass in that address. Okay, so we have an address starting at some address aligned to 4 bytes, and we just return that value. So then when we increment by 1, we're now moving on to the next multiple of 4. And if we are offset by 2, we still get the same address because we're jumping to the next address that's aligned to 4. Same with 3, 4. And then when we get to 5, then we have to jump, well, relative to the start, we have to jump by 8 bytes instead. Okay, and I will publish this code so you can have a play with that if you like. But I think we always get questions on how this dotted line 2 works in MIPS, so I thought I'd use this to highlight that as well. Okay, so this is the fun one, the XOR. Okay, so it's a little bit like OR, except the resulting bits are set to 1 if and only if exactly one of the original bits are 1. So if we have 2 1s, we end up with a 0. And if we have two zeros, we end up with a 0. It's only when we have 1 0 or 0 1 do we end up with a 1 or a 1 in the final result. Okay, this is used heavily for cryptography, flipping bits, checking for bits that don't match. Okay, so bit mask with the XOR operator. So for any given bit value x, what is x not to the power of x XOR 0? So we're essentially flipping that. So if this was 1, if this is 1, we'd be flipping that bit. But because it's not 1, x just passes straight through. Okay, whatever x was, that'll pass straight through. If it was a 0, then then 0 XOR 0 is going to be 0. And if it's a 1, 1 XOR 0 is going to be 1 as well. It's going to be 1. But if we have x XOR 1, so now this is going to flip the bit for us. So if we had a 0 and we're XORing with 1, then we end up with a 1. And if we had a 1 and we're XORing with 1, well, now we have two 1s, which means that our result is going to be 0. So whatever x was is going to be the negation of that, the not of that. So for example, we have our nice example here of OX13 for our x, 7 as our mask, and we're going to XOR the mask. And our mask is highlighted here in orange. So for all the bits in orange, we're going to flip the bits. So we had a 1 in the original, we end up with 0, 1 in the original, we end up with a 0, 0 in the original, we end up with a 1. So we flipped all of those bits. So what would happen if we applied this mask again? What do you think? So if this was our so we can read this upside down then actually. So if this was our input and this is our mask and we're XORing, we're flipping the bits again, so we end up right back to where we started from. Okay, so little exercise. So evaluate the following here. What's 5 and 6? And then what is 5 and 6? Okay, so this is the logical AND. So we have non-zero and non-zero, so that's going to be non-zero, non-zero. And then we have 5 and 6. So this is a bitwise operator though, so we need to look at the bits involved here. So we have, I like to draw it like this. 5 will be 0, 1, 0, 1, and 6 will be 0, 1, 1, 0. So bitwise AND, we get 1 here, 0, 0, and 0. So 1, 2, 4. So the result here will be 4. And a little joke here, how many beers did the software developer drink? I'll leave this one to you guys. Okay, so we've covered AND, OR, XOR, and the bitwise NOT operator, but there is a demo that I wanted to bring forward. I was planning on doing this later, but I'm going to bring it forward a little bit. So we have our XOR program. So all of these, I won't be publishing these because they're all present in that code section of the website. Okay, but XOR is a fun little program. Okay, so we're expecting an argument here on the command line and a value to XOR. Okay, we turn that string into a value, of course. Check that it's in range, and then we have this interesting loop here. So we're going to grab a character from the command line, sorry, from user input. And for each character, we're going to XOR that with the value that was provided on the command line, and we're going to print that character. Okay, and what will we XOR it with? 42. Oh, might be nice if I provided some input from standard input. Okay, so we're going to echo hello world and pipe that as standard input to this program. And the argument to the program is OX42. I think Andrew's example was much nicer than this. That's kind of garbage. I believe it was hello Andrew. Still have garbage. Oh, I'm using the wrong. Okay, so this is somewhat more readable than this. So let's stick with the example that Andrew's using. Okay, so for each character here, we've taken the XOR of the byte value of that character, and then we've printed it to the terminal. Okay, and if we choose a different value, as you saw, 41, we'll get a slightly different result. So this is the foundation for cryptography. I mean, it's a little bit more complicated when you get to real cryptography, but this is the general idea behind it. So the only way to understand what this is saying is if you have the key that was used to encrypt it. So if I pass this, as we saw before, if we XOR it again with the same value, we should end up with the same result. So we're taking hello world from standard in, we're going to XOR each character with 41, and then we'll repeat that process, and we should get back to exactly what we had before. Okay, so hello Andrew. If I try a different value, I just get a different set of garbage out. So I need to know what that key was that was used to encrypt it in order to draw meaning from this. So you can imagine in this example I have only 256 different combinations to do. So I could just repeat this 256 times, and when I get something that seems like it makes sense, then that's probably the key that I should be using to decrypt it. But for true cryptography, it becomes a little bit more complicated than that. Alrighty, so we've done the basic bitwise operators, and the ones we have left are the shift operators. I always seem to get ahead of schedule in the online tutorials, the online lectures. Okay, so let us cover those. So the left shift, so this is going to take a value and a small positive integer. Okay, and it's going to shift each bit x positions to the left. Okay, so in this example, this bit is shifted to here, this one to here. So because we're shifting by 2. Okay, so shifting 2 places. Okay, and these bits on the end, they just go nowhere. They disappear. Okay, and the same with this one here. And these ones here, they need to come from somewhere, but they're always filled with zeros. Okay, so new bits are inserted on the right, and they're always zeros. So keep in mind that the result here always has the same number of bits as the input. When we do a left shift, we're not gaining bits and we're not losing bits. Okay, so what does this mean mathematically to left shift a number by, in this case, 2? Or what would it mean to left shift it by 1? Okay, so if we have a binary 1 and we're shifting that by 1 place, then we are left with this binary number here. So and the result here is 2. For the next one we're shifting by 2, so that's just an extra place here. So now we're 4, then we shift again, we get to 8, and we shift again, we get to 16. Okay, so what we're doing is we're shifting from this column here. Will I use a pen? We're shifting from this column here, which was 2 to the power of 0, into this column here, which was 2 to the power of 1. So we're effectively multiplying by 2, or 2 to the power of what our shift value is. If we shift by 2, we're moving from our 2 to the power of 0 to our 2 to the power of 2. Okay, because we're shifting by 2. So we're effectively, in this case, multiplying by 2 to the power of 2. This will multiply by 2 to the power of 3. And this one multiply by 2 to the power of 4. We have an example. Oh, I forgot to grab that one. Use my trusty wget. Okay, so again, taking a command line argument, that's going to be n. And we're going to work. Oh, sorry, this is just checking whether it's going to be out of range or not. Okay, so we take our 1 and we're going to left shift by n, and we print bits of it, of course. Oh, so I forgot my trusty print bits. Okay, so 2 to the power of 1 is 2. And we can go on experimenting with this. What happens if we do minus 1? We get this bit up the top set. Interesting. Okay, so what? Alright, I don't want to spend too much time on that one, because I think we cover that a bit later on. Okay. So can you program x times 6 without multiplication? So multiplication is another operation that can be expensive for a CPU. Can take a number of cycles to execute. So can you program x times 6 without using multiplication, just using bitwise operators? How do you think that would be done? Geez, I rocket through these slides when I'm streaming online. Okay, so we can split this apart. X times 6 is really just x times 4 plus another 2 x's on top of that. Okay, so x times 4 plus x times 2. And each of these can be implemented by these bitwise shift operators. Oh, excellent, we got some answers. So the x times 4, there must be a lot of lag in the video. So the x times 4 becomes an x shifted by 2. And then we add on x times 2, that can be represented by x shifted by 1. Okay, so the reverse here, instead of left shifting, we to right shift. It's the same principle here. Um, there is one complexity to it though, but basically we're right shifting. In this case, we're shifting by 2. So all these bits, oh, that's shifting by 1. Can't undo. Can't erase. There we go. Oh, so all of these are getting shifted to the right by 1, by 2, sorry, in this case. And these ones here, just like before, these just disappear. Okay, so we're not gaining any bits by shifting, we're not losing any bits. And in this case here, we're shifting in zeros, okay, into the spaces that are, um, are no longer occupied. So we get no new 0 bits inserted on the left. So this is true for unsigned types. Okay, for a signed type, depending on the operator, so the sign bit can get extended over here when we're shifting to ensure that we we maintain a negative number. So this right shift operator is typically used for taking bits one at a time. So if we want to loop through these individual bits, then we would take the right shift, sorry, by 1. And I have a little example of that in this mysterious print bits file that we've been using. Oh, actually this one isn't a great example because this one calls this function get nth bit each time. But you can see what we're doing here is we're taking a value, we're shifting it by n, and then we're going to apply a mask so that we only have the value that was in that nth bit, and we return that. And that's how this function is printing each individual bit of an integer. So implications of right shift. So what does this one mean mathematically? Well, I think if shifting left means multiplying by 2, then shifting right must mean dividing by 2. So if we have this expression here, so this would be 1, 2, 4, 8, 16, because every time we go up a bit, we multiply. Excellent, thank you, divide. I hate this lag. I much prefer to be in the lecture theatre. So 16. So we shift right by 1, we end up in the 8 column. If we shift right by 2, we end up in the 4 column here. 3, we end up in the 2's column. By 4, we end up in the 1's column, to be left with 1. So divide by a power of 2. Okay, but what about situations like this? We lose bits, right? So we have 0111, and when we shift right, we lose that least significant bit. We end up with 0011. Okay, so this was 7, and now we end up with 3. But this is exactly what happens with integers anyway, right? So if we're dividing 7 by 2, we truncate the value, so we don't end up with 3.5. We end up with just 3. So important, we're not rounding here at all. We're just chopping off whatever the decimal value is. Alright, so issues with shifting. Okay, so shifts involving negative values, they may not be portable, and they can vary across different implementations. So you can imagine these CPU architects, they want to optimize their CPU, and shifting by negative numbers is not very meaningful. You could argue that, well, if you shift right by a negative number, then you're actually shifting left, and if you're shifting left by a negative number, then you're shifting right. But just use the right shift operator. So typically in your CPUs, the negative shifts, or the negative shift values, they'll actually be interpreted as a unsigned value. Remember, it's the CPU, it's not the value that gives it meaning, it's how you use them that gives it meaning. So the CPU is basically just going to cast this negative number to a positive number, and it's going to shift in the wrong direction as far as it can. So always use unsigned values and variables when shifting to be safe portable. Sorry, the other thing is, so the behavior of that, so it typically would just cast the negative value to a positive integer, but that's not necessarily true. It's undefined behavior, so we leave it up to the CPU architects to decide what the appropriate action is there. Okay, shift bugs. We all like bugs. Bugs can be really interesting, especially when you're programming in assembly. Well, yeah, we don't care about warnings. It's just a warning. Well, we better have a look at this program first. So we have a number of undefined shift operators here. Okay, so we have a negative number. So when we shift right, it's not actually defined for the negative values. Yeah, and we're shifting left. The shifting left negative value is undefined. Okay, and this will be int max. Yes, we're looking at 16-bit value, so this will be int max. I'm not sure why they didn't use the limits.h constants here, but yeah, if we're shifting int max left by 1, so then that's going to be multiplying by 2, and that's undefined as well. Oh, yeah. So it typically would produce a negative value. Yeah. And this was the warning that we saw from the compiler to say, well, we're shifting beyond the bounds of an int. And I might show you how to fix that in a minute. But what we can do is cast this to a 64-bit value before we shift, and then that's okay, because now we've told the compiler there's enough bits there. Okay, and we only print the first two. That's no fun. I think we need LD there. Okay, so the first one we have -1 shifted to the right, and on this particular machine we still are left with -1. So for the second one, we're shifting -1 to the left, we end up with -2. So that seems like it's doing the right thing on this particular CPU. And our maximum value, shifting it by right, remember this is a signed value, so we're actually shifting into that signed bit. Right, so that's where the problem lies. We have a positive number, but when we do the shift, we're shifting into the signed bit. So in this case, third one, so we end up with a minus value there. And this fun one here. So this one was okay though, so we're shifting by 32 bits, and I wish this was printed in hex, so I could tell you whether that was 32 bits or not. But we'll trust that it is. and it's a little freebie. So this is giving us a warning about left shift count being greater than the width of the type. We fix that here by casting this one to be of a larger type, but we can also add that to our constant as well. So if we use UL, this is saying by default this will be an int, so we're saying we actually want this to be an unsigned long, so a larger unsigned integer, and it will treat that constant exactly like that. So when we compile it, we shouldn't get the warning anymore. Alright. Well, I think we're almost through, so I might give everyone a break and we can look at these in a bit more detail. Pokemon's a really interesting one, and might take me a little while to get through. So I'll give you guys 5 minutes. We'll come back at 7:10. Alright, let's get back to it. Yeah, so I don't have that many slides left to go through. So, like, there was a question that I missed in chat though. I don't understand bitwise. So maybe this is the best example. So it's saying that these operators here are operating on individual bits of our, I'll say, registers or just values. Okay, so we can effectively treat each bit in these registers as independent. So our operations are bitwise. Okay, so the result of this does not depend on any other bit in these values, and the same with this one. It only depends on the corresponding bits in the same column. Alright, so Pokemon. I think we've done, wait, I think we'll start with set low bits. Yeah, the difference between signed and unsigned int. So we have these values, these binary values here, and so they can represent our numbers for us, and it would make sense that you know, increasing numbers like all zeros will represent 0, and then if we have 1, 0, 0, 0, that would represent the number 1, and so forth. And for our unsigned integers, this continues up to our maximum value, which occurs when all of these bits are set to 1. Okay, but for unsigned integers, sorry, for signed integers, what we actually do is we cut. It's not a very good whiteboard. So we have, for example, on the bottom here, all zeros, and at the top, all ones. And here we will have, you know, in the middle, some value like this. Okay, and this will represent our unsigned integers. I won't convert these. Okay, so at some point as we're counting up, okay, we get to this value in the middle here, which has just that most significant bit set, and then we continue on until we get to our maximum value here. So what we do for, so this is how we represent unsigned. That's a bit small. Sorry about that. So this is how we would represent unsigned integers. So starting at 0, then we'd count up to 1, and then we'll keep going until we get to this roughly middle value, which has that most significant bit set, but everything else 0. And eventually we count up to a maximum number where we have all the bits set, and that's our maximum value. So these are our unsigned numbers. For signed numbers, signed integers, what we effectively do is, I should have put some more in here. what we effectively do is we take this top half of the available representations for numbers and we chop those and we stack them underneath. Okay, so we have half as many positive numbers, but that's allowed us some representations of these numbers to use as negative numbers. Okay, so the best thing about this approach is that 0 still represents 0, 1 still represents 1, all the way up to this number here. Okay, they all represent the same numbers, and if we had a number like this in an unsigned value or a signed value and we cast it, it will come out to be the same value. Okay, but then we have this kind of strange representation underneath, and the main reason for that is if we have a 0, if we were to subtract 1 from 0, that's, oh sorry, I need to get rid of that, that's no longer max, this is now the max. This is now our min. So if we have 0 and we want to go 1 less than 0 to find -1, then the ideal representation for the CPU architecture is to just follow the same subtraction algorithm. So in this case we have all zeros, so with the standard subtraction algorithm you progressively look to a more and more significant value, and in this case in the CPU, when it gets that final bit, it will effectively put an imaginary bit at the end here. So it will take from that imaginary bit and in the process fill the ones all the way back. Just like if you had 1,000, you would take that 1 from the 1,000 and you would fill 9s all the way back, in decimal at least. Okay, and then we continue on subtracting until we get to a minimum value here. So this keeps it really simple for the CPU, not so much for us reading it, but then we get interesting behavior as well when we're taking a negative number and we cast that to be in an unsigned int. You're welcome. Yeah, so what does knowing signed in binary mean? Like, why is it important? So again, if you've got the case where you've got a negative number and you're casting that negative number to an unsigned int, you can then reason about why you've got such a strange number, such a large number as a result there. It's because you're taking this as an unsigned int, this is -1, but then when you cast it, you're basically just taking these bits and you're telling the compiler, yeah, just treat this as an unsigned number. So this now becomes, instead of -1, it becomes the maximum possible value of your unsigned integer. And this can cause lots of problems in your code, right? If you thought that you were subtracting by 1, well, now you're actually subtracting by a lot. Alright, I think we'll get back to the lecture. There was a really quick recap for you. Whoop, and a spoiler. Okay, so we were going to... Wait, let me have another look. Get nth bit we covered. Did we cover get low bits? We mustn't have. thought I had been through and collected all of these. Right, so again, we're taking an argument from the command line here. So argument 1, we need to turn that from a string into an integer. We're checking that it's in range. Okay, so we take our mask of, so we're going to initialize this mask to 1. Okay, and what we're going to do is we're going to shift that bit in that mask up by n bits. And I keep talking about how when we have one bit set, when we subtract 1, we clear that bit and we backfill all the ones. So that's exactly what we're doing here to create a mask that is n bits long. So if I were to say, let's make it 1 bit long, so it gives me a mask of 1. Okay, well that wasn't very interesting. What about a mask of 2? So this is a bit like our align 2, so it gives us 2 bits set. And what else can we do that's interesting? 31. Okay, so just following this process through, if we had mask of 1, we're shifting by 31, so that's going to end up over here. And then when we subtract by 1, take this 1 and backfill all these 1s. What if we do 33? It didn't like, oh, there's an assertion in there. That's no fun. Wrong window. Assertions are no fun. Let's see what happens. Okay, so 33. So this is interesting. So we end up with 1 when we choose 33. So it was lucky that we had that insert there to make sure that we weren't doing something silly. About 34. So it's starting to, I have a feeling that for this particular CPU, the mask value we are, we're just chopping off the high bits and using the low bits there. Or is that? So when we rotate this out, and we could go further with this and print the intermediate values to check, but sometimes maybe I get a little bit too curious. I hope that you do that in your own time. Just explore what happens. Oh, so there was one other thing I wanted to show here. So in our, that's where they went. No, they didn't. Okay, so we had our align 2. So let's copy that to align in general. Oops. Okay, so we've made a copy of that. Let's edit this copy. So we now want a we don't want to have a function for a line 2 and a line 4 or a line 8. Right, we want something generic. So we can specify the number of bits that we want to align in here. Okay, and this is getting a little bit more complicated, so why don't we say, so we're masking with this data type here, UN pointer t. So we should probably, if we're going to create a variable for our mask, we should probably use the same type. Okay, so instead of hard coding the value here, we'll do what we were doing in that previous example. Okay, so again, we shift that one up a certain number of bits, and then when we subtract one, that becomes a 0, and we backfill all the ones. And now we can use this mask here. Still need the not in there. How do we represent the 4? Okay, so does this still work the same way? No, because we need to change where we call the name of the function that we're calling as well. And I guess it would help to add an argument. So with 2, it should behave exactly the same as the previous code. Okay. So this is as before, giving us an aligned address that is aligned to a multiple of 4 to satisfy alignment requirements of our integers. But if I go back here, if I change this to a 3, so this should give us alignment to 8. Okay, so here we were aligned to 8. When we add 1 to our address, when we try to align it, we have to go to the next multiple of 8. And again, when we get to 59, we have to go to the next multiple of 8 there. So now we have a function here that can take an arbitrary value for the alignment requirements. Again, we're using a lot of bitwise operators here to realize this function. Okay, now we get to play some Pokemon. Okay, so I assume that everyone knows Pokemon. The massive phases of crazes, collector cards, games. You have Pokemon Go as well, which I guess is technically a game, but I think that's like a class of its own. Okay, and in Pokemon, you have these Pokemon that you keep in these dark little balls and bring them out to fight, and they all have different properties associated with them. So you might have fire type Pokemons. So in this program, we're going to represent this as number 1 or bit position 1. You might have a fighting type of Pokemon, so we're going to represent that as a 2 or a 1 set in bit position in the next bit, and etc, etc. Okay, so each of these is going to be represented by a different bit in our 16-bit value to describe the type of this Pokemon. Okay, so our Pokemon here is where it gets a little bit strange. So it might be, we might have a bug type, but it might be a poisonous bug type. Okay, and it might be a poisonous fairy bug type. So by ORing all these together, we are setting all of these bits that represent these different types. And it's a little bit strange because you might say bug type and a poison type and a fairy type, but when it comes to these bitwise operations, we don't use the AND in this case, we use the OR operator. Okay, so this program was just going to print these bits and sorry, it prints the bit representations of the hexadecimal numbers that were above, and then it's going to print out the bit representation of a Pokemon, and it's going to check whether our Pokemon is a poison type and say that we're poisonous if that's the case, scary if we're a ghost type. This is a representation that you haven't seen before. So just like we had plus equals, if you want to increment a variable, you'd use plus equals and then some constant. We can do the same with our bit operators. So the OR equals would be the same as our Pokemon equals our Pokemon, and then OR in the ghost type. And the same with the AND here as well. So in this case, for the poison type, there's a bit that represents the poison type. To remove that, we need to create a mask, because what we really want to do is it's not so much that we want to remove this type, it's that we want to keep everything except for this type. So we take the bitwise negation there to flip the 1 for this poison type into a 0 and all the other bits into a 1, and when we mask it, we will keep all of the type attributes apart from this poison type. And then we print our Pokemon again. Can't find the Yoki. I always forget these print bits. So remember this undefined reference, this means that the compiler was able to compile main, but then when it came to linking it all together, and in your assembly you have these labels, and these labels are used in places and defined in places. In the final step, the linker, LD, is trying to find the label for print bits, and it can't find it. So we have to give it an additional C file to use. Okay, so this is the bit representation of the bug type. So we should only see 0s and 1s here. And the poison type and the fairy type, and you can see that none of these bits are overlapping. They're all different types. And our Pokemon type, so when we OR all these together, so it is merging all of these bits from these different types into the one value. Okay, and then we find that the poison type is checked, or the poison type bit is set. So we report that this Pokemon is poisonous, and I forget what we did from there, but apparently whatever we did, so we set a bit here. I'll have to try and remember what that bit represents, and we cleared a bit here. That one is clearly the poison type. So we're now just scary. Oh. I think I lost you for a minute, but you should be back. Okay, so it wasn't scary before because we only printed poisonous. Then we added the ghost type and removed the poison type. So then we don't print poison anymore, but we do print scary. Okay, so that was Pokemon. Okay, I think that's the end of our demos. So now some exercises. What I love about programming is when you get these exercises and you're trying to work them out by hand, all you have to do is copy and paste that into a C program to work out what the answer is, to check your answers. And for everyone who's stuck around, is a little cheat code. If we have a decimal number, if you set your calculator into programmer mode, you can also see the hex, octal and binary representations of that number. But unfortunately this isn't available to you in the exam, so you might need to, if you want to do these translations, you might need to write a little program to do that for you. Can we get the calculator in the exam? Unfortunately not. Okay. I think there is actually already an example of this. At some point I think it'll be easier just to write another version of it. That's how it went. So you could use this as a very simple calculator for just doing the base conversion, right? So you just punch in your number, either in decimal, hexadecimal, binary, or octal, and then you can just use, all you have to do is use the different formats here for printing the value. So %U for decimal, X for hexadecimal, O for octal. Binary is a bit more complicated, but from the hexadecimal you should be quite easily be able to go to binary. Okay, so will we need to know bitwise for the assignment? Not for the MIPS assignment, but hopefully in the second assignment to come, that will be heavily focused on bitwise operations, because I mean these assignments and these assignments and these tests, we're not really trying to measure your understanding and your knowledge. We're really just trying to give you practice to prepare you for the exam. The reason we give marks for it is to motivate you to actually do them. So there's likely going to be some bitwise in the exam because it's quite a big part of this course. So the second assignment will hopefully give you a lot of practice in bitwise so that you'll have no problem in the exam. But just keep in mind that you don't have AI or ChatGPT or Google in the exam. So if you're using it for these practice exercises that we give you, then you might have some trouble in the exam. Because in that case, you're learning how to use those AI tools instead of learning how to solve the problems. Where was I? Okay, so we have X and Y. Oh, yeah. Okay, so for bitwise, it's always more useful to view these numbers in binary. So 5 is 0, 1, 0. I think Notepad is the way to go for this one. X equals OX55. So that would be OB 0101 0101. Y equals OXAA. The reason on why I always know off by heart what A is because I'm so used to starting from A. Sorry, so when it gets to the higher digits, I always have been using A as a reference, so I always find it easy to remember what A is. Okay, so we have, let's keep that down there, X and Y. Okay, so everywhere these are the same, let's copy them down. Everywhere these are the same, we'll end up with a 1 in the answer. Remember, we're taking these one bit at a time. So least significant, well, we'll start with the most significant bit. But that'll be 0 because only the bottom one set, only the top one set, only the bottom one set, only the top one set, and so forth. None of these bits, if we were to AND these together, none of them would be set. We would end up with nothing. XOR is always more interesting. Okay, so remember we get a 1 in the result if and only if only one of these bits is set. And that is the case for all of these bits here. Either we have a bit in X set or we have a bit in Y set. So these would all be 1. Okay, so for the left shift, so we're left shifting X. So this is an interesting one. So this is X here. So we're shifting this by 1. So we actually end up with Y here. So 55 left shifted by 1 is going to end up with hexadecimal AA. And Y shifted by 2. The bottom one is Y. I think the best way to do this so that you don't make a mistake, because it's still quite a low number, would be to shift by 1 twice. Okay, remember when we shift to the left, we fill in these gaps with zeros. And we need to do that twice. So from our bit representation, we end up back at A. And then 8, A8. So on the right hand side here, why don't we start with G actually? So if we were to OR these together, so if we take each of these pairs of bits independently, if at least one of these bits is a 1, then the result will be a 1. And that's the case for all of these bits here. There's either one set, there's one set in each of these values and they alternate. Okay, so x shifted by 1. Oh. So that's the value for x. But then that extra 1 there just falls off the end. In fact, easier way of showing this would be just to add the 0 in the front there and take the 1 off the end. Okay, and the last one. So this is y, and we're shifting this by 2 to the right. Okay, so I'm going to take note that these are unsigned numbers. Okay, so using that trick before, this is y again, but if I'm shifting to the right, I'm inserting 2 zeros up the front, and that means that these 2 will fall off the end, because whatever bits we start with, that's the number of bits we end up with. Okay, so that was F. Okay, so I think I just have 1 or 2 more slides, because I'm sure you're bored of looking at C. You probably want to look at some MIPS again. So these are the bit manipulation instructions in MIPS. So these should start to be familiar to you. So AND, we have OR, we have XOR, and we have the equivalents that take an immediate value instead of a register. Okay, and then we have NOT here. So this does what we expect it to be. It's a bitwise NOT. But this is a pseudo instruction. I wonder how that would be implemented. Okay. And we have this this is one that you haven't seen before. So this is a NOR. So this is just saying not OR. So whatever the result of the OR would have been, we take the bitwise inversion of that. So RS or RT with the bitwise not in the front. So what do you think the pseudocode for the not instruction would be? Okay, well, the excellent thing is that we can always just punch it in and check. Few too many arguments. Okay, so this is actually going to take the 0 register and it's going to OR it with the register that we're interested in. Okay, so remember when we're ORing 0 with anything, we end up with whatever that anything is unchanged. Okay, and then because this instruction is also taking the bitwise NOT, so the result of this is just a NOT operation. So this is how the CPU architects have been able to provide a more complex instruction instead of the much simpler instruction. So you can do a lot more with this. And if you wanted that simpler instruction, you just use this magical 0 register in the place of one of the registers. Okay, and the MIPS instructions for the shifts. Okay, so the V here stands for the value, so value in the register. So these are kind of inverted, right? So normally where we have an immediate value, we would have an I. I believe this is just because normally when we have these shift operators, we're using an immediate. So it makes more sense to have an extra character for this instruction if we are using the R type. Okay, so here we have, so this will stand for shift logical left. Okay, so essentially that's just a left shift, and I'll get to what logical means in a minute. And shift right logical, so this will shift right. So these logical shifts are just going to add zeros in their place. And we have a right shift here, shift right arithmetic. Okay, so this is going to shift in a 1 if it's a negative number to preserve that sign. And yeah, so we have the equivalent for the immediate. So notice there's no shift left arithmetic because that would be the equivalent of the logical left shift. Alrighty, so 2 minutes left. So what did we learn today? So we did a recap of this integer representation. And if you at all want further clarification on the integer representations, please do reach out, start a discussion in the forum. So we covered the end of bitwise operators. So that's the end for both integers and bitwise in terms of lectures. So next we're going to be looking at floating point. So how is that represented in a CPU? Okay, and as usual, yeah, if you have any course related questions, reach out on the forum, please. And any admin related questions, email address is cs1521@cse.unsw.edu.au. And please keep in mind that I am on that mailing list as well. So if you want to reach me, it's best to just email cs1521 because we do have a team of admins monitoring that email address who and they might be able to respond quicker than I can. All right, thanks so much. I'll hang around for 6 minutes for any questions. But unfortunately, the lag in the video makes it difficult to answer the questions in real time. Any questions, anyone? Alrighty, let's leave it at that then. Thanks for stopping by and devoting your evening. Yeah, I will see you on Monday. Take care.